Shivsankar Shukla, and today I will be discussing with you all about an interesting and learning episode of B.Pharm on the unit of X-ray spectrometry second, which is too important unit of the pharmaceutical analysis third, 8th semester. Let's start our episode related to the module 1, 1.1, 1.2, 2, 2.1, 3, 4, 5 and 6, while taking a look at what we are going to learn today in this regards. Coming to the modules, module 1, introduction, module 1.1, lattice arrays and various lattices, module 1.2, a two-dimensional lattice, module 2, diffraction and wax equations, module 2.1, problems with X-ray crystallography, module 3, powder X-ray diffractometry, module 4, X-ray diffraction pattern of the cubic system NaCl, module 5, applications, and last but not least module 6, conclusion. Now coming to the module 1, introduction. X-ray was discovered by the German physicist Roentgen and found that unlike ordinary light, X-ray were invisible and they traveled in straight lines which affected photographic film in the same way as light. X-ray were also more penetrating than light and could easily pass through the human body, wood, thick pieces of the metal and other opaque objects. In 1912, the exact nature of the X-ray was recognized, and the same year the phenomena of X-ray diffraction by crystals were discovered. The discovery provided a new method for investigating the fine structure of the matter. Now we know the X-ray are electromagnetic radiations of exactly the same nature as light, but of the very shorter wavelength, that is 1 Armstrong. So X-rays are ideal to explore interatomic distances which are typically of that order. Now coming to the module 1.1, lattice arrays and various lattices. Crystalline materials differ from the amorphous materials in that in the previous there is order in the collection of the molecular contents, whereas in the latter there is no order or at best a tendency for a shorter range order. The wedding of the atoms, molecule or ions inside a crystal occurs in a symmetrical manner, and in addition this symmetrical arrangement is repetitive. A most important common features that crystals may share in the manner in which repetition occurs. This will be expressed in a common lattice array. Coming to the module 1.2, a two-dimensional lattice. Pick up any position within the two-dimensional lattice in figure 1a and note the arrangement about this point. The chosen position can be indicated by a point, a lattice point, in view of the repetitive arrangements. There will be a two-dimensional array of identical positions, and if these are also marked by a point, a two-dimensional lattice will result if the points are adjointed. This figures shows a real three-dimensional crystal lattice structures. When crystal structures are represented by the lattices, it transpires that all crystals break down into one of the 14 three-dimensional lattice arrangements. Bravis demonstrated mathematically that there are only 14 ways in which repetitive symmetry can occur, and the 14 lattices representing the way in which repetition can occur are referred to as the Bravis lattices. Now coming to the module 1.3, unit cell. The unit cell is the smallest structure that repeats itself by the translation through the crystal. We construct these symmetrical units with the hard spheres. The most common type of the unit cells are the face oriented cubic, the body centered cubic, and the hexagonal close packed. Other type exist particularly amongst minerals. The simple cube SC is often used for didactical purposes. No material has this structure. These are the most common types of the unit cells: simple cubic, body centered cubic, and face centered cubic. The PLF. Important properties of the unit cells are the types of the atoms and their radii are cell dimension, side A in cubic cell, side of base A and height C in HCP in terms of R. N number of the atoms per unit cell for an atom that is shared with m adjacent unit cells. We only count a fractions of the atoms 1 by m. Cn the coordination number, which is number of the closest neighbors to which an atom is bounded. APF the atomic packaging factor, which is the fraction of the volume of the cell actually occupied by the hard spheres. APF is equals to sum of the atomic volumes divided by the volume of cell. A unit cell can be any unit of the lattice array which when repeated in all directions and always maintaining the same orientation in space generates the lattice arrays. There is no unique way of choosing a unit cell. For example, each of the cell A to D in figure 3a is OK. However, the cell favored by the crystallographers is the one of the smallest volume that displays all of the symmetry of the lattice. The cell C and A are the preferred unit cell for the lattices of figure 3a and 3b respectively, and figure 3a and figure 3 shows the unit cells for the lattices. Unit cell types and the 7 crystal system. From figure 3a and b we got cubic system. If the cubic system is there, A is equals to B is equals to C, where alpha is equals to beta is equals to gamma is equals to 90 degree. In the tetragonal system, A is equals to B is not equals to C, whereas alpha is equals to beta is equals to gamma 90 degree. In the orthorhombic system, A is not equals to B is not equals to C, alpha is equals to beta is equals to gamma is equals to 90 degree. In the monoclinic system, A is not equals to B is not equals to C, whereas alpha is equals to gamma is equals to 90 degree and beta is not equals to the 90 degree. Triclinic system, A is not equals to B is not equals to C, whereas alpha is not equals to B is not equals to gamma is not equals to the 90 degree. In the rhombohedral or trigonal system, A is equals to B is equals to C, means that alpha is equals to beta is equals to gamma is not equals to the 90 degree. In the hexagonal system, A is equals to B is not equals to C, whereas alpha is equals to beta is equals to 90 degree, but in gamma it will be 120 degree. In general, 6 parameters are required to define the shape and size of the unit cell, these being 3 cells age length, conventionally defined as A, B and C, and 3 angles conventionally defined as alpha, beta and gamma. In the strict mathematical sense, A, B and C are the vectors since they specify both length and directions. Alpha is the angle between the B and C, beta is the angle between the A and C, and gamma is the angle between A and B. The unit cell should be right handed. Check the cell above with your right hand. 4 simple points on the crystal lattices. First, every crystal system has a primitive Bravais lattice. 2. The distribution of the lattice point in a cell must be such as to maintain the total symmetry of the crystal system. Thus, the cubic system cannot have a C-type cell. 3. The fact that a unit cell meets the symmetry requirements of the crystal system does not guarantee its inclusion within the crystal system. This could result if the lattice it generated could be equally well represented by a unit cell type, which is already included within the crystal system. The C-type cell for the tetragonal system, see figure 4, provides a good example. This figure 4 provides the C-type cell for the tetragonal system. Module 2, diffraction and the Wax equations. Max von Laue was the first to suggest the crystals might diffract X-rays, and he also provided the first explanation for the diffraction observed. However, it is the explanation provided by the Wax that is simpler and more popular. Since a beam of X-rays consists of a bundle of separate waves, the wave can interact with one another. Such interaction is termed interference. If the wave in the bundle are in phase, that is, their crests and troughs occurs at exactly the same position, the same as being an integer number of the wavelength out of the phase. N lambda is equals to V is equals to 1, 2, 3, 4, etc. The waves will interfere with one another and their amplitudes will add together to provide a resultant wave that has a higher amplitude, the sum of all the waves that are in the phase. Read figure 5, the waves in the bundles are in a phase. If the wave are out of phase, being off by a non-integer number of wavelengths, then destructive interference will occur and the amplitude of the waves will be reduced. In an extreme case, if the waves are out of phase by an odd multiple of 1 by 2 lambda in bracket 2n plus 1 bracket closed by 2 lambda, the resultant wave will have no amplitude and thus be completely destroyed. Figure 6 shows the waves in the bundles are out of phase. The atom in crystals interact with X-ray waves in such a way as to produce interference. The interactions can be thrown off as if the atoms in a crystal structure reflect the waves, but because a crystal structure consists of an orderly arrangement of atoms, the reflections occurs from what appears to be planes of atoms. Let's imagine a beam of X-rays entering a crystal with one of these planes of atoms oriented at an angle of theta to the incoming beam of monochromatic X-rays. Monochromatic means one color, or in this case one discrete wavelength as produced by the characteristic spectra of the X-ray tube. Two such X-rays are shown here, where the spacing between the atomic planes occurs over the distance d. Rays 1 reflects off of the upper atomic planes at an angle theta equals to its angle of incident. Similarly, ray 2 reflects off the lower atomic planes at the same angle. While ray 2 is in the crystal, however, it travels a distance of the 2a further than ray 1. If the distance 2a is equals to the integral number of the wavelength and lambda, then rays 1 and 2 will be in phase on their exit from the crystals and constructive interference will occur. Figure 7 describes the degree of diffraction of rays and spacing between the atomic planes. If the distance 2a is not an integral number of the wavelength, then destructive interference will occur and the waves will not be as strong as when they enter the crystal. Thus, the condition for constructive interference to occur is n lambda is equals to 2a. But for trigonometry, we can figure both what the distance 2a is in the terms of the spacing d. between the atomic planes. A is equals to d sin theta or 2a is equals to 2d sin theta, then n lambda is equals to 2d sin theta. This is known as Bragg's law for X-ray diffraction. What it says is that if we know the wavelength theta of the X-ray going into the crystal and we can measure the angle theta of the diffracted X-rays coming out of the crystal, then we know the spacing referred to as d spacing between the atomic planes. D is equals to n lambda divided by 2 sin theta. Again, it is important to point out that this diffraction will only occur if the rays are in phase when they emerge, and this will only occur at the appropriate value of n 1, 2, 3 etc. and theta. In theory, then we could reorient the crystal so that another atomic plane is exposed and measure the d spacing between all atomic planes in the crystal, eventually leading us to determine the crystal structure and the size of the unit cell. Now, coming to solving a crystal structure by single crystal diffractions technique. The crystal must be single crystal. Bragg's equation specifies that if a crystal is rotated within a monochromatic X-ray beam such that every conceivable orientation of the crystal will relative to the beam is achieved, each set of the planes will have had the opportunity to satisfy the Bragg's equation and will have given rise to reflection. In order to solve a crystal structure, it is necessary to record a large number of the reflections. This implies accurately measuring their intensities and recording their direction with respect to crystal orientations and initial X-ray beam direction. Many experimental techniques have been devised to achieve this. The steps involved in the crystal structures determinations are summarized in the flow chart. In this flow chart, we select a suitable crystal, then we go for the crystal system and unit cell dimensions, then we will go for the full data set collection, then go for the Weber's lattice arrangement, then we go for the space group, then in continuation this go for the construct an electron density map, and then locate atom positions, and then finally structure refinements. Diagram of an area detector X-ray data collection system. The first crystallographic data collection systems used photographic methods. These were replaced by automated diffractometers which measures reflections one at a time. Typical data collections took several days. Modern systems use area detectors which measures 100 seconds at a time. Figure 8 shows the diagram of an area detector X-ray data. The crystals is oscillated over less than 2 degree, while an image is collected, then rotated by a same amount and oscillated again. The process is repeated over a total range of about 180 degree. Each image is exposed for less than 100 seconds. Thus, if readout time is ignored, total data collection time is often less than 3 hours. Module 2.1 Problems with X-ray crystallography. Locating hydrogen atoms. Hydrogen atoms make extremely small contributions, and for this reason X-ray crystallography is not a good technique for accurately locating hydrogen atom positions. If the location of the hydrogen atom is of specific interest, example in the study of the hydride structures and hydrogen bonding interactions, use has got to be made of the much more expensive and less available technique of neutron diffraction. The theory of neutron diffraction is very similar to that for X-ray diffraction, but an essential difference is that hydrogen atom scatters neutrons as effectively as many other atoms, and for this reason they can be located with good accuracy in the structure determination. The need for the single crystals. In order to carry out detailed X-ray structure determination, it is essential to have a crystal of the material in question. Many compounds cannot be crystallized and thus are not amenable to diffraction studies. There are also commercially important materials such as glasses and many ceramics which owe their unique properties to their amorphous nature. Being amorphous, no long range order, the structures of these materials cannot be investigated in detail by diffraction techniques. Low temperature structures determination. When X-ray data are collected at low temperature less than -150 degrees centigrade, thermal ellipsoids are smaller and better defined, and we want length, so very little variation with temperature. Now coming to the another module 3, powder X-ray diffractometry. In practice, this would be a time consuming operation to reorient the crystal, measure the angle theta and determine the d spacing for all atomic planes. A faster way is to use a method called the powder method. In this method, a mineral is grounded up to the fine powder. In the powder are thousands of the grains that have random orientations. With random orientation, we might expect most of the different atomic planes to lie parallel to the surface in some of the grains. Thus, by scanning through the angle theta of the incident X-ray beam from 0 to 90 degree, we would expect to find all angles where diffraction has occurred, and each of these angles would be associated with a different atomic spacing. A crystalline powder sample will diffract X-ray, but since the orientations of the individual crystals are random, the data set produced is a plot of intensity versus diffraction angle or Bragg angle theta. Here the sample is sitting on a flat plate and the plate is turned about the center of the diffractometer at half the rate through which the counter moves. This is the Bragg scan method. Notice the plot contains 2 theta on the x-axis and X-ray intensity on the y-axis. Figure 9 shows the diffractometer's beam path in the theta by 2 theta mode. Now coming to the usage of the X-ray powder diffractions. In general, powder diffraction data are unsuitable for solving crystal structures. Some advances have recently been made using the Rietveld method. However, this is far from trivial and it works best in relative sample cases. It is very difficult to be sure that the unit cell is correct as the reflections overlap and are difficult to resolve from one another. Important advantages and use of the powder diffraction. First, the need of the grow crystal is eliminated. 2. A powder diffraction pattern can be recorded very rapidly and the technique is non-destructive. 3. With special equipment, very small samples may be used, that will be the 1 to 2 mg. 4. A powder diffraction pattern may be used as a fingerprint. It is often superior to an infrared spectrum in this respect. 5th, it can be used for the qualitative and often the quantitative determination of the crystalline components of the powder mixture. 6th, powder diffractometry provides an easy and fast method for the detection of the crystal polymorphs. Powder patterns are provided when a drug is being registered with the FDA, Food and Drug Administration. Polymorphs are different crystal forms of the same substance. Calculations using X-ray powder diffraction pattern. that will be determined by 1 by DHKL square equals to H square divided by A square plus K square divided by B square plus L square divided by C square. This is the expression for an orthorhombic crystal. For the tetragonal system, it reduces to 1 by D square HKL equals to H square plus K square divided by A square plus L square divided by C square. And for the cubic system, it further reduces to 1 by D square HKL equals to H square plus K square plus L square divided by A square. Now coming to the module 4, X-ray diffraction pattern of the cubic system NaCl. This structure shows the sodium chloride crystallized in the space group Fm 3 meter. With stoichiometry formula from the unit cell for the sodium chloride structure, in the case of central, sodium ion will be the 0, chloride 1, faces 6 by 2 for sodium ion, and for the chloride 0, edges 0 in case of sodium, and in case of the your chloride ion 12 by 4, in the corner in the case of sodium ion 8 by 8, and in case of the your chloride ion 0, total in case of your sodium ion will be the 4, and in the total in the case of the chloride ion will be the 4. That is why this figure, this table shows the X-ray angle 2 theta pattern of the sodium chloride from the unit cells. Now coming to the module 5, applications. Studies of the universe and rocks, cosmic X-rays, 3D images of the body tissues. 3 techniques involves completed topography (CT) and completed axial topography (CAT). Provided physical information rather than chemical information. X-ray absorption, useful for the medical radiography for the location of the bones. Defines the shapes of the arteries and capillaries. Were used for the detection of the cracks and holes in the belts and joints for the bridges, aircrafts, buildings. Were used for the measuring the thickness of the thin metal films. Used for the determining the liquids levels in the sealed vessels or the pipes. Now another example, X-ray fluorescence for the qualitative identification of the elements present in the samples. Permits multi-elements analysis of the alloy, where we also use for the both liquid and solid samples. Used for the solvents should contains elements with low Z, that is water, HC or nitric acid. Another use, X-ray fluorescence. Intensity of the fluorescence is used for quantitative analysis. They were be used for flat surfaces, are required for the quantitative analysis. C is equals to K into I into M into S, where C is concentration of elements, K is the operating conditions and is function of the spectrometers, I is the intensity of the measured signal, M is the inter-element effects, absorption and enhancement effects, S is the specimen homogeneity. Another use of XRD, non-destructive techniques. It provides the detailed information on the structure of the crystalline samples. Diffraction pattern are unique for each compounds. It will be used for the determination of the degree of crystallinity of the semi-crystalline solids. To determine the disorders in metals and alloys, it will be used for the single crystal XRD for the exact position of the each atom in a crystals. Now coming to the limitations of XRD, it cannot identify amorphous materials, cannot be used for the traces analysis, it will be difficult to identify mixtures due to the overlapping peaks. Now coming to the module 6, that will be the conclusion. Dear students, now we were going for the conclusion of this particular X-ray spectrometry second. With all these informations, here we come to the end of the 2 days lectures. Hope we have understood about X-ray spectrometry. X-ray spectrometry has a wide application in analysis of the crystal, its shape, size, orientations, etc. The topic we have discussed today is frequently applied for analysis of the different drug sample and could be well remembered by the visiting nearby drug testing laboratories for understanding its practical aspects. So, dear students, this is Dr. Shiv Shankar Shukla taking leave from you with the hope that you enjoyed and understood today's lecture. Till then, keep study. Goodbye.